This presentation is delivered by the Stanford Center for Professional Development.
Okay, let's get started. So today's segment, come on. Interesting. This is really an interesting development. In '99, a robot playing volleyball, and this was developed by a company, Toshiba, which is remarkable. So,
robots in games and competition. Beach ball volley playing robot. Japan.
a lot of people.
Future robots are going to work in your houses and hospitals with humans. Toshiba has developed a beach ball volley playing robot as a demonstration of such a human-friendly robot technology. We consider that it is essential to interact with robot using everyday words such as, let's play volleyball. For the everyday word commands to work, the robot needs to measure the target's relative position with respect to the robot position, to know the mechanics and procedures of the tasks, and to have a good database for the environment and the target. With an integrated sensor feedback technology, we have demonstrated a robot which can play beach ball volley with an opponent, pick up a ball from the floor, and shake hands with a human by only one respective everyday word command. The robot uses two head-mount CCD cameras to measure the target ball position in every 1/60th seconds. The cameras always track the ball. The operator commands the robot to pick up the red ball. Then the robot starts to search for the red ball on the floor. After finding the ball, it moves above the red ball. Then it checks the arrangement of all the balls to make a plan to pick up the ball. When the robot finds that the arrangement is too difficult to pick up the red ball, it pushes the green ball aside and checks the ball arrangement again. Then it picks up the red ball. We use visual servo control at the rate of 1/60th seconds to achieve this picking up motion. This is the robot view. After pushing aside the green ball, the robot checks the arrangement again and approaches the red ball by using the visual servo control. Also, to show the human friendliness of the robot, it can shake hands with a human. It has a tactile sensor in its right hand to start handshaking. It also has a 6-degree of freedom force torque sensor at its wrist to readily respond to the young lady. See you.
Okay, so I'm not sure who was shaking the hands, the human shaking the hands of the robot or the robot shaking the hands of the human. I wonder if you know why this whole environment is white. Yeah, I mean the vision is working, picking the color, and using color you can go fast. So what is the challenge here?
If you were to have any color environment, you would possibly mistake a blue background for a blue ball.
No, I meant what is the challenging problem in this demonstration? What was the most difficult part in this demonstration?
Depth perception.
Perception, depth, and
Tracking the ball.
tracking the ball. Tracking the ball is very important because you have to predict where you're going to hit. By the way, students from this class last year worked on a project in experimental robotics to duplicate this with the Puma, and it was a lot of fun. So you have the camera and you're tracking the ball. You need to predict where the ball is going to be, and then you place, because your arm is not going to be positioned correctly with the right orientation unless you do that prediction. And this is how human work. Human do a lot of prediction. I mean, the feedback is really slow, but the prediction is amazing, and that's how you can do this. There are also other aspects of the problem. They were talking about the grasping, which is a very simplistic problem in here because they are using really two hands as a gripper for a large object. So the grasping part is, but it was remarkable. In '99 they managed to do it. So that was quite interesting. 97, 98, Honda came with Ashimo, and that was another big achievement in robotics, getting a robot to walk upstairs, downstairs. We will get to talk about this later, but it was the time when suddenly, just before the turn of the century, we started to see all these results coming from the maturing of technologies that were bringing vision, good mechatronic integration to make robots much faster, to do tasks like walking stably and also performing dynamic skills like hitting the ball back. Okay, the Jacobian again. Well, today we're going to be able to look at a mechanism like this one and see the Jacobian. I promised you that you will take a look at the robot and you will see the Jacobian. We're going to do it. And like in few minutes you will see like all the columns coming in place and everything. So, this is the explicit form of the Jacobian. Last week we saw a messy, complicated way of looking at the Jacobian or extracting the Jacobian by propagating velocities from the base to the end effector, computing the total linear and angular velocities as a function of the joint velocities recursively, and then by doing this computation you have the expression of the Jacobian somewhere embedded in that final answer of your linear velocity and angular velocity. So if you separate the joint velocities, you will find what are the element of your Jacobian matrix. But you don't have any idea about exactly what is the structure of this Jacobian matrix, what would make it really singular, how the mechanism joint axis affect angular velocity and linear velocity, etc. So now what we're going to do is we're going to go to each of the joint axes, prismatic or revolute, and analyze its impact on both the linear velocities and angular velocities. And by doing this analysis, we are going to be able to immediately see how these joint axes are going to map to the Jacobian, in which columns and in which way. And then basically we can do the reverse. We look at the joint axis and we will see the Jacobian. So this is what we're going to do. All right. So let's start with a joint. Pick a joint. I don't know. This one? Let's pick this one. So I'm drawing the vector omega I representing the angular velocity generated by q dot I. So the direction of q dot I is along this vector, and its magnitude is proportional to theta dot. Okay? So this is basically theta dot zi, which we are calling omega I. Well, to span all the degrees of freedom, we need another joint that is prismatic, and I think we have one over there, prismatic joint. So let's take, oh, well, we'll come later. So we just are writing what is omega I. And here is the prismatic joint. This prismatic joint is along joint axis J, so along Zj, and the velocity I'm measuring is this capital Vj, which is proportional to what? It is proportional to d dot j. D is the variable, prismatic variable along the axis Zj. So the prismatic velocity for joint I, or we keep I, Vi is Zi q dot I. In the case of prismatic, q dot is d dot. And in the case of revolute, it is theta dot. You remember the epsilon I. Okay? Now, the question that we should answer is the following. If we go to the end effector, so let's go to the end effector and say, I'm interested in computing the impact of the linear velocity on the linear velocity of that revolute joint and that prismatic joint. So I'm going to put prismatic joint and revolute joint, and we are forming this table. So on this table, the question is, what is the contribution of a prismatic joint moving at velocity Vj on the linear velocity at the end effector? You see the end effector point is right here. So at this point, what if I have, everything is still. If I just have Vj, what would be the end effector linear velocity? So we need to answer that question. Then we will place it here. I'm sure everyone now is looking at the notes. Don't look at the notes. Place it here. And then we're going to find the impact on angular velocities. So think about it. This joint is translating with this velocity. What would be the linear velocity due to Vj? Not all at the same time. Anyone?
If you just added it, it would just be V.
What will be Vj? What is the impact on the linear, the angular velocities? None. So the Vj is transformed directly to the end effector, and we will find that the prismatic joint will have a contribution on the linear velocity identical to the prismatic joint velocity along the same direction of that velocity. On the angular velocity, a linear velocity will not change the angular motion of the end effector, so there will be no effect. And I'm not going to hit return because I'm afraid that we will see revolute. So let's think about revolute. I don't remember the order. So now it's a little bit more complicated, but remember the apple. That is, we are going to look at the effect of this omega I at the end effector. What is the linear velocity due uniquely to omega I? So, do you remember the apple? So, what information we need? We need to locate the end effector point, distance from the axis. So we really need to introduce a vector that connect joint I to the end effector. We will call it PIN, connecting the origin of frame I to the origin of frame N. So let's make sure the none is okay, perfect. So now on the revolute, we do this connection, and now we need to compute the linear velocities due to omega I. So that is going to be so you're rotating and you have the vector. How do we compute that linear velocity?
Cross product.
Cross product. But that's not enough. You have two possibilities, right?
Omega cross B.
Omega cross P. Everyone agrees? It is omega cross P. So omega I cross PIN gives you the contribution of revolute joint I on the end effector linear velocity. Okay? What about angular velocity? We said the angular velocity is not affected by the prismatic. Is it affected by the revolute? What is the contribution? Omega I itself. So if we have a revolute joint, the total angular velocity is going to be the sum of all the omega i's. And everyone is going to contribute with the same angular velocity. Now, the total angular velocity, you walk through, you take your epsilon I, and following the type prismatic or revolute, you can compute the total angular velocity. So if we had a prismatic, a robot with prismatic joints only, what would be the total linear velocity? We call it V. The total linear velocity is going to be equal to the sum from I equal 1 to n of, with epsilon, I need something, because I'm going to use something like q dots. Epsilon. So epsilon I was equal to 1 for prismatic and equal to 0 for revolute. So sum I from 1 to n of epsilon I so all prismatic joints, come on. I mean, if you just have prismatic joints, we are talking only about V1 to Vn, right? You just add them together. But can you write it with the epsilon? Is it epsilon I or epsilon I bar? Epsilon I times the VI's. Okay. Right. If we had revolute joints only, the linear velocity would be, okay, someone else, I think from this side, someone was trying to answer. Anyone? You were trying to answer? The V. Okay, I have only revolute joints. And I have those joints starting from 1 to n. What is the total velocity due to those revolute joints? Would be the sum of all of these from 1 to n. But I'm just looking for the epsilon. Sum from I equal 1 to n of, very good, epsilon I bar multiplied by this. Now if we have mixed joints, then the linear velocity will be epsilon I VI or epsilon I bar omega I. Now you understand this? Yes.
It's 0 when it's revolute and 1 when it's prismatic.
Right. So this epsilon is equal to 1 for prismatic joint and equal to 0 for revolute joint and epsilon bar is the complement of epsilon, which means that this would be equal to 1 if the joint is prismatic. This would be 0, or this would be 0, and then that would be 1. Either one or the other. Okay? Now, what about the total angular velocity? It's going to be, if I have prismatic joints, if we have prismatic joint, you use epsilon I multiplied by 0, he said. He's like sitting like this. I have to, yeah, 0, yes. Epsilon I by 0. So only revolute joints will contribute, and that means omega is equal to the sum from I1 to n of epsilon I bars, all these omega i's. So omega is just this expression. Okay? All right, so here is omega and v. So here, so over there you have v, the total linear velocity, and omega, the total angular velocities. Now, I don't know if you see the Jacobian yet, but we're not far. We're very close. How do we go? So now we have an expression for v, an expression for omega, and the question is, how can we extract the Jacobian? So what is the Jacobian doing? The Jacobian matrix is defined as the matrix that connects q dots to v and omega. So you have two parts in this matrix, jv and j omega. jv is the matrix that connects v to q dots, right? And j omega connects omega to q dots. The question is how we go from here to finding jv and j omega. Could you help? What do we need to do? So right now I'm expressing v as a function of vi and omega I. Omega as a function of omega i's. What do we need to do? Yes.
Omega I is for z q dot.
Okay, so.
Or, sorry, yeah, z q dot, and then vi is with
zi q dot as well. And if we do that, then we will have an expression here and an expression here that is linear on q dots. And this is a sum from q dot 1 to q dot n. Basically, you are just moving through the columns of the Jacobian matrix. So we substitute in those expressions vi with zi q dot, omega I with zi q dot. And if we do this, what's going to happen? I'm going here to substitute this with zi q dot I, and there with zi dot q. Okay, let's do it. Come on. Oh, magic. Now, what do we have here? We have q dot i's, the same, but depending on the type of the joint. If the joint is prismatic, I'm using zi, and if the joint is revolute, I'm using zi cross pin. And here, if the joint is revolute, I have simply zi. Let's start with the simplest form. So the simplest is this one. And my question is, what is the first column of the Jacobian matrix j omega? So this will be the j omega. This is a sum, right? So j omega, the first column of j omega of a robot whose first joint is revolute. Okay, I hear Z1, I hear 0. Oh, Z1, 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 everyone. So the first column of a robot that is first joint is revolute will be Z1 for j omega. What would be the first column of JV for that robot, same robot? I have to go up here. Any volunteer to?
P1 cross P1N.
Excellent. So if the first joint is revolute, it would be 1, 1n. That vector connecting joint 1 to joint n. My robot is completely prismatic. Could you tell me what is JV? So the first column would be Z1, second column Z2. Isn't that beautiful? Z3, Z4. That's your Jacobian. What about j omega for a robot that is completely revolute? Z1. Could it be any simpler? I think now you will start to see the Jacobian. So if we take this expression and really expand, this is what is happening. V is now a linear combination of the joint velocities going from the first to the end. And now if you take the coefficient of those q dots, you can write your JV. And JV is saying that if the joint is prismatic, the column is just the Z axis. And if the joint is revolute, it's the cross product between that Z axis with the vector connecting the joint to the end effector. Okay? And if we expand the second expression, we are just looking at revolute joints. So a prismatic robot will have 0 columns, and a revolute robot will have all its columns. So it will be all these as just Z axis. So it is, you're just writing 0 or Z. Okay? All right, well, basically this is it. Now you combine the two, JV and J omega, and you get your Jacobian. So this recursive computation we were doing as we propagated and we computed the velocities and went to each frame and made sure that the frame, the expression is done in the same frame and transform it back to the 0 frame. All of this now is written here explicitly, so you have this explicit form that is actually not expressed in any frame yet. We said the Jacobian, this Jacobian, j omega, is function of Z1, Z2, Zn. We didn't say in which frame. If you decide now about the frame, we have to decide where we express these vectors, right? So when we express vectors, we have to express the Jacobian in a given frame, 0. All the vectors have to be in frame 0, all the columns. Over there, you are doing cross-product computation. Well, the cross-product computation should be done in the same frame. It could be frame 72, but then you have to transform it to the same frame where you're expressing your matrix. So you can do it in frame 2, for instance, and then take it back to frame 0. So this is a very general form expressing the Jacobian in a vector form. And then the question is where you're going to need your Jacobian computation. And you do that computation by expressing all the vectors in that frame. So this Jacobian, which is JV and J omega, can be also simplified further if you already computed your forward kinematics. Because JV, if you remember, JV is related to the linear velocities. So if I'm using spherical coordinates, I cannot just differentiate spherical coordinates and get linear velocity. But if I'm using Cartesian coordinates, then basically I can directly differentiate that vector and obtain JV. So if you have x, y, and z computed already, where can we find x, y, and z? In the forward kinematics. Where can we find it? In which column? In the fourth column, and you get x, y, and z of the point that is expressed in some frame. And you can take the differentiation of that and your Jacobian matrix, if this vector was expressed in frame 0, the position xp, now xp is x, y, and z of the end effector point, then you are taking the differentiation with respect to q1, q2 to qn. And that is also your Jacobian associated with linear motion. And this Jacobian should be identical to the one computed from Z1 cross P1N, P1N, P2N to the last one. All right. So again, there is no commitment yet where XP is expressed. So to go to a frame, what is important is to make sure that everything in relation to all these vectors describing the Jacobian is expressed in the same frame. So this is a vector representation of the Jacobian. And if we go from the homogeneous transformation, if we computed the homogeneous transformation, then we should be able to do this computation immediately. So once you have your homogeneous transformation, you should be able to extract your Z1, Z2, Zn, and XP, and just do the simple differentiation and find your Jacobian matrix. Now, most of the time we express the Jacobian in frame 0. So in frame 0, this would be simply expressing all these vectors in frame 0. Well, it could be frame n. It could be maybe sometimes you need it in frame n for some task and you want to transform it to frame 0. So we need to understand also the relationship between the Jacobian in different frames. But let's first look at these vectors. And for these vectors, the information about Zi in frame 0, so let's say I'm interested in Z7 in frame 0. So where can I find this information precisely? So Zi is the Z vector of frame I. So Zi in frame I is equal to what? What? 0, 0, 1. So any Z in its own frame is going to be 0, 0, 1. How can we find 0, 0, 1 and transform it to frame 0? What are we going to use? I'm sorry? I cannot hear you very well. You have to speak louder.
Transformation between
So we take the transformation from frame I to frame 0. Which transformation you want? Basically the rotation. You take the rotation matrix, the 3 by 3, which is in the homogeneous transformation. So you take the rotation from frame I to frame 0, and you can compute your Zi in frame 0. So Zi in frame I is always constant, right? So we call it Z. I mean, this is the Z vector 0, 0, 1. And as you said, we take it from frame I to frame 0, which means that essentially we need to pre-multiply 0, 0, 1 by the rotation matrix from frame I to frame 0. What does it mean? Think now about this 3 by 3 rotation matrix. And you are multiplying the rotation matrix by 0, 0, 1. What are you doing there? What is the result if you multiply the 3 by 3 matrix by 0, 0, 1? You are picking the last column. So basically, this information is found in the rotation matrix, in the third column of the rotation matrix 1 to 0, 2 to 0, n to 0 for the revolute joints. Okay? So now we have this form, and we are going to try to apply it to a relatively complicated robot, the Stanford Scheinman Arm. And on Wednesday, I will bring it in the lab so you can see it, and we can look at some of the properties related to the singularities and those axes, and you can see the prismatic joint. But let's rely on the picture, so you still have to imagine the robot. And what I want you to do is to see now the Jacobian. Can you see it? No? All right, maybe if I give you a drawing of it, it will be better. But before that, let's go and summarize what we have seen. We said to compute V and omega, we compute this Jacobian from its two components, JV, the block JV, and the block J omega. V is JV connecting Q dot to V, and omega, J omega connecting Q dot to omega. And the first column, I mean the first block JV is either the ZI of that joint or the cross product of this ZI with the vector IN. Okay? The omega and the J omega is simply the ZI vectors corresponding to revolute joints. All right. So you see this? Because now I'm going to ask you to give me the Jacobian for this robot. And this is the schematic of the robot. And you can see here the Jacobian is empty. You need to fill it. And I hope you're not looking at your notes or you don't have the answer. So, all right. Let's see if anyone sees what should go here. Now, you have to match it with the joint of the robot and their types, okay? Do you understand those types here? Joint 1 is revolute or prismatic? Revolute. Second and third, and then the rest is revolute. Okay, here we go. Here, Z1. Okay, here, Z2. Who said Z3? I heard Z3. No, you said 0? Okay, 0. 0, 4, 5, and 6. Okay. What about this one? First one. It's a revolute joint. The first one is 0. Revolute joint, it is Z1 cross P1 or 0 because they are coincident, but P1, 2, N. In this case, N is that green frame. It is on frame 3. So really 2 to 3. What about this one? So 1, 2, 3, 2 to 3. Yes?
3. Why not 6?
It could be 7 if we attach the frame at any point. Often for the end effector, we attach the frame, additional frame. But for this computation, we said we will do the computation at the wrist frame, which is the frame. In this case, it turned out to be the frame number 3. Identical. The origin of 3 is identical to 4, 5, and 6. The same frame. So this one would be Z2 cross 2, 3, and here Z3, 0. So you have Z1, Z2, 0. There should be a Z3. It pushes up. It goes up. The Z3 goes up and you get 0. So when you have a prismatic joint, you're getting a 0. Otherwise, you have the revolute joint. So let's check. So you get Z3. So the next column is going to be 0 because now we are measuring the distance from 3 to 4. It's the same point. Yes?
All these Z's, what they represent, are they the Z-axis for each frame?
Okay. This is very important. If we don't know the Z-axis, come on. My computer is. What? Just 1 second. Let's go back to the beginning. So the Z-axis is the joint axis itself, along which we are having this rotation. And this is when we go to the frame themselves, like when we go here, this is Z0, and if you remember, there was Z1 attached to frame 1, and Z2, we are seeing here Z6. So these are the Z-axis along the joint axis. And those are the Z's that we are talking about. And we are measuring the rotation about the Z-axis, and we are measuring the prismatic motion or the linear motion along the prismatic joint ZI. So when we were computing prismatic joint 3, the motion along this direction is coming from along that joint. Okay, everyone sees this. This is important. If you don't see the Z-axis, yes, you have a question.
It's always 0, 0, 1, right?
In its own frame. But in frame 0, it's whatever it is. So Z3 in frame 3 is 0, 0, 1. And this is what we call the Z. And what we saw is that when we go and express this in frame 0, we need to transform this vector to frame 0, as well as all the vectors should be expressed in frame 0. Okay, now why do we have 0 here? So this should be Z, what? Z4 cross P 4 to 3. I mean, basically, we're going to that same point, which is 0. So here 0 and here 0. Here we said we have Z1, Z2, 0, Z4, 5, and 6. Okay? All right. Can you really feel what is happening on this Jacobian compared to your mechanism? Do you understand it? Although we are in the same frame, the origin at the same point, rotations are going to add. So there is columns for omega. For the linear velocity, there is no effect of joint q dot 4, 5, and 6 on the linear velocity. But angular velocity, it is there. The rotations are described directly by the z-axis of the joints. And when you multiply by the q dot to compute v and omega, you are multiplying here by q dot 1, q dot 2, q dot 3, 4, 5, and 6. Okay? Yes?
Just double check. You could have also said Z1 cross P16.
Yeah, I mean, if we called this the end effector frame in frame 6, yeah, it will be 6. And if it was another frame, 7, at the end effector, it could be 7. I just write it here, knowing the fact that 3 is the same point as all the following origins. Okay. Now we're going to do this computation. Now we're going to find this matrix. And so maybe that's what it was doing, just like, thank you. How can I turn it off? I think my computer was like suffering trying to update something. All right. And it must do it every time I have a lecture. I think the camera just like looks and find me and look at the black and white and then just, oh, he's here, so let's do it now. All right. So it's quite simple, but please pay attention now. I'm going to show you how we can start from the beginning, right after you did your frame assignment, and compute both forward kinematics and your Jacobian in one shot. So let's walk through it. So we know how to do this, right? You did the homework and you know how to do it. And this is D2, a constant, right, over there. So I'm going to use D2, D3, and we are going to use those variables, and we are going to express our transformation as a function of theta 1, theta 2, D3, 4, 5, and 6, which are the Qs. So what we are going to do from here, we are going to compute the homogeneous transformations. Every rows correspond to a homogeneous transformation that is computed from these expressions going from frame I minus 1 to frame I. This is I. And now I'm going to write it down. So when we computed all of these, we do this multiplication and we find the forward transformation from frame n to frame 0. Okay. Now, the way you do this computation, the steps you're going to take are very important in order to obtain your Jacobian in a given frame at the same time as you are doing your forward kinematics. So this is the transformation from frame 1 to 0, 2 to 1, 3 to 2. These are coming directly from the formula. You're not doing any multiplication. You're getting 1 to 0 from the row, first row, second row, third row, fourth, fifth, and sixth. Okay? So I'm just applying the formula to all the DH parameters. And if we had another frame attached to the end effector, there will be 7 to 6. And that one will be constant. It will not be depending on any joint. So here is what we're going to do. If we are going to express our Jacobian, and this is what we do most of the time in frame 0, because we would like to find our velocities in frame 0. So what are we going to need? We are going to need all the vectors in frame 0. So in particular, we need the zi vectors in frame 0, which means we need the rotation, the third column of the rotation matrix vector that take us from frame I to frame 0. So for the first z, z1 in frame 0 is where? z1 in frame 0 is right here. It is 0, 0, 1. So when I do this computation, I will compute 2 to 0 by multiplying 2 to 1 by 1 to 0. I get 2 to 0. And that gives me z2 in frame 0. What is z2 in frame 0 from here? Minus sine 1, cosine 1, and 0, the third column. And this is z3 in frame 0. So these are very important in computing the Jacobian, but also are going to be needed. So when I'm doing the multiplication, I always form from I to 0. I will not compute 3 to 1 and then multiply it by 3 to 0. I will be wasting too much time. I will just go 1, 0, 2, 0, 3, 0, 4, 0, 5, 0. Okay? And this way you are getting directly all the vectors in frame 0. So you can do this for all of them. And this is the last one. This is what? Z6 in frame 0. Okay. So where is your Jacobian? Basically, you already have it. It is already here in the homogeneous transformation. The J omega 6 column, fifth column, fourth column, third, second, first column. Actually, the third is 0, but this z is needed in the top of JV, so it will go up. Yes?
What about the p vectors?
Okay, we're getting to the p vectors. Okay, so the j omegas are already there, all the columns. And if the robot is prismatic, the same thing, we have the Jacobian JV. Yes?
You were saying to save time, not multiply the T10 and T21 and the incremental one. So do we just figure out the columns of T10 and T20 directly from just inspection?
Well, actually,
just pick the third column?
Yeah, but actually you are going to need the final transformation to compute the orientation of the robot. So you need this column and this column for the description of the orientation for the forward kinematics. So you need to do the multiplication, but what I'm saying is do multiply starting from, you start from, you have 1, 0, but then you have 2 to 1, then 3 to 2. Do not walk by multiplying from this side, 3 to 2 by 2 to 1, then multiplied by 1 to 0. You multiply 2 to 0, you obtain 2 to 0 from 2, 1 multiplied by 1, 0. And now you use this matrix multiplied by the next one. You go from 3 to 0. And this way, you have these intermediate computations that are going to be needed in addition to your result. You still need the final matrix because this is your homogeneous transformation. Okay. Any questions about, this is just to make sure that you have these intermediate vectors expressed in frame 0. Yes?
Can you go back 2 slides?
2 slides.
I guess, it was when you were doing the formulas to compute is it from I minus 1 to I, or to, like, you have 1 on the slide?
Yeah, I said it is a mistake.
Oh, okay. Sorry.
And I don't know if I should change it now or later, but every year I have this. It was a mistake from a long time ago. So let's see if we can change it. No. So, yeah, I need to go here, and I think I can change it. All right. Okay. Now it's correct. Thank you. All right. So now what I was saying is, as you compute your homogeneous transformation, make sure that you have those intermediate vectors that you will need for the Jacobian. Now, okay, are you still with me? Your attention? All right. Look at the last column. Look at the last column in this transformation and compare it to the previous one, to the previous one. It is identical, right? Do you know why? We have the same point. So actually this is the same as we have here. When we reach frame 3, in fact, we reach the end effector point. Okay, so the question is, how are we going to compute now as we go through this? How are we going to compute JV? Well, if we go and compute JV, we have two ways of doing this, either by computing the vector P from 1 to n and express it in frame 0, or the frame where the z is expressed, or, as I said, what these represent? X, y, and z, the Cartesian coordinates. So you have already the Cartesian coordinate in your homogeneous transformation. So actually you don't need to compute the p's. You just differentiate this and express your JV as a function of the partial derivative of x, y, and z with respect to q1. You get the first column, q2, second column, etc. So just to check if you are following what I'm saying, could you give me, we are on the first vector of the Jacobian JV, and I would like to find the third element of the first column. Third element of the first column of the Jacobian JV. So what are you differentiating? Okay, it gets you 0. And the first element will be differentiating the first one and second one. Okay. What is the third column of JV? Let's differentiate. C1, S2, S1, S2, and C2. Okay. Can you check whether your answer is correct independently? Yes, go ahead.
It's just a Z column.
It is this. It is because this is a prismatic joint, joint 3. It should be identical to the Z3, which is here. So when you differentiate with respect to D3, you obtain this column. Do you see that? Because both computations should give you the same answer. So the third column, we know the third column is simply Z3. But if you still differentiate, you get Z3. Okay? Now you trust it? All right. So basically, this computation of the Jacobian is already in your homogeneous transformation. I mean, you are computing at the same time you are computing your forward kinematic x, y, and z. And all what you need to do is to extract your z vectors in the appropriate frames and fill your Jacobian. And for the JV part, you are going to use this differentiation. And you have your Jacobian. So the Jacobian matrix for the Stanford Scheinman Arm, once you computed your homogeneous transformation from frame 6 to frame 0, you have your forward kinematics. In here, you have x, y, and z. In here, you have the rotation, so you have direction cosines. You have all the description. Here you have your direction cosines, x, y, and z. Direction cosines, first column, second column, third column. And now you can take the intermediate steps where you computed the zi's to fill your Jacobian matrix. And the Jacobian matrix is here. Yes?
Two columns?
The first two columns we differentiated this expression with respect to Q1. This is x. This is the first element, 1, 1. In the first column, second element is differentiation of this with respect to 1. And this with respect to 1. So what we are doing, we are taking x, y, and z and differentiating with respect to Q1. That will give you the first column. This column corresponds to the contribution of joint 1. So you differentiate with respect to Q1. This column is the contribution of joint 2. You differentiate with respect to Q2. The third column is with respect to Q3, or because this is a prismatic joint, this could be obtained directly from Z3 in frame 0. Yes?
This XP, is it the fourth column of T06?
Right. This is the fourth column of T06 in here. So if you read this and you manage to read this, you will obtain the same thing. XP is copied from X, Y, and Z in the homogeneous transformation if we are selecting Cartesian coordinates. Okay?
Q1. There's no like D1 in the first expression, so
Yeah, fortunately, otherwise it would be a problem because we have C1. So what is C1? Maybe the confusion is that you don't see the dependency on Q1. What is C1? And S1? What does it mean? Could you explain what is C1 and S1? Anyone can help me finding what is C1?
It's cosine of Q1 or cosine.
It is cosine Q1 for joint 1, which is revolute, which means cosine theta 1, the variable theta 1. So Q1 is in the cosine 1, and C1 means cosine the angle Q1. So when we differentiate C1 with respect to Q1, what do we get? If we just differentiate this first element, element of the fourth column, you differentiate with respect to Q1. Are you there with me? Are you there with me? Could you differentiate the first element with respect to Q1 now?
so the cosine would just be minus sign.
So you differentiate with respect to Q1 and you have cosine 1. That would be
Minus sine
1 and
minus cosine 1 p2.
very good. Okay, do you understand that? Everyone understand what these? Probably this is maybe not clear. S1, when we say S1, C1, S2, C2, we are referring to the variable Q2. Okay? All right. So this is the matrix. All right. So you see, after all, the Jacobian is not that complicated. The Jacobian is simply these columns associated with your z-axis for the lower part related to rotational motion for revolute joints. For prismatic joints, it is the same axis. And for the other joints, I mean for the linear motion, all what you are doing is a simple differentiation of your x, y, and z. And that gives you the answer for the Jacobian matrix. Now, what is interesting about the Jacobian matrix is the fact that you cannot just go and use the matrix without really making sure that you are in the right configurations to perform a task. Because for many of the interesting configurations for some robots with a wrist that has problems like the singularity, you are going to not be able to move about some axis. You are locally going to lose the ability of rotational motion for about some of the axis depending on that configuration. So there is the notion of kinematic singularity that you can directly examine from this matrix. And those singularities correspond to a singularity into the matrix itself. So if we take a 2-degree of freedom robot, if we can have the camera on my arm, please. So if you take a 2-degree of freedom robot and you are moving now in space, in this plane I can move anywhere, right? Instantaneously I can produce any displacement. But if I move and stretch to the end of the workspace, do you notice anything now? I cannot move along this axis. So the axis could be like this or like this, but I cannot move instantaneously along this axis. There is no displacement delta theta 1, delta theta 2 that produces a component in this direction. And this is a singularity. What happened in this configuration is the fact that now the two columns of your Jacobian matrix became dependent. So when those columns become dependent, you are going to lose rank. The matrix is not full rank. This matrix is 6 by 6. And we like it when it is full rank. But if two columns become dependent, immediately you lose rank and you lose the freedom to move. So on Wednesday, I will bring the Stanford Scheinman Arm here, and we will be able to examine another type of singularity related to the wrist point, and the fact that joint 4 and joint 6, when they are aligned, you lose the ability to rotate about this axis. And that makes it really hard to perform motions in those locations. Not only in those locations, but also around those locations. The problem of singularity is that when you come close to the singularity, the matrix becomes L-conditioned. Numerically, it's L-conditioned. If you want to compute the inverse, it is going to give you large numbers. And that is, if you want to do a small displacement in delta x, you will need large displacement in delta q to produce those motions. So we will examine this, and we will talk about the kinematic singularities on Wednesday. See you then.